Good morning, everyone. Myself, I'm Tanishka from EEE Department Section A. Today, I'm going to talk about the topic magnetic properties and crystal structure of sputtered CoFe films from the course Engineering Physics. Magnetic properties and crystal structure of sputtered CoFe films, a comprehensive exploration of how physics vapor deposition creates advanced magnetic materials for next generation spintronic applications. Introduction. The promise of CoFe alloys in spintronics. Why CoFe matters. Cobalt iron CoFe alloys represent a critical advancement in magnetic material science. These binary systems combine the desirable properties of both elements, cobalt's high saturation magnetization, and iron's cost effectiveness and abundance. Together, they create a material with exceptional magnetic performance that exceeds either component alone. CoFe films have emerged as the material of choice of spintronic devices, where control over electronic spin becomes as important as controlling charge. Their high magnetization, low coercivity, and excellent terminal stability make them ideal for applications demanding reliable magnetic behavior. Sputtering. The fabrication method explained. Magnetron sputtering is a physical vapor deposition (PVD) technique that energetically removes atoms from a target material and deposits them onto a substrate. An argon plasma is created by applying a strong electric field between a cathode, target, and anode substrate. Argon iron strike the CoFe target, ejecting atoms, though momentum transfer. These atoms travel through the vacuum and condense on the heated substrate, forming thin film with controllable thickness and composition. First, plasma generation. Argon gas ionized by electric field creates energetic ions. Second, target sputtering. High energy ions bombard CoFe target, ejecting atoms. Third, atom transport. Ejected atoms transverse vacuum chamber towards substrate. Fourth, film deposition. Atoms condense and crystallize on substrate surface. Experimental setup. CoFe film deposition and characterization. Our experimental framework combined precise deposition control with comprehensive structural and magnetic characterization. CoFe films were deposited on silicon 100 and glass substrate using a magnetron sputtering system equipped with 2-inch CoFe target. Film thickness was controlled by adjusting deposition time, while substrate temperature was maintained between 250 degrees Celsius and 300 degrees Celsius to study thermal effects on crystallinity. First, X-ray diffraction (XRD), structural phase identification and crystalline quality assessment. Vibrating sample magnetron (VSM), magnetic moment and hysteresis measurement. Transmission electron microscope (TEM), nanoscale morphology and grain structure visualization. Magneto-optic effect (MOKE), surface magnetic properties and domain dynamics. Crystal structure analysis (XRD) and TEM insights. X-ray diffraction revealed that CoFe films exhibit a body-centered cubic BCC structure consistent with the FeCO phase diagram. Samples deposited at room temperature displayed board diffraction peaks indicating fine crystalline grain size 0 to 15 nm As subtract temperature increased to 300 degrees Celsius, peak sharpening and narrow occurred, demonstrating enhanced crystallinity and gain growth. The 100 peak dominance confirms preferential growth along this crystallographic direction. Room temperature films, fine grain structures 8 to 15 mm, broad XRD peaks, amorphous like character, high defect density. High temperature films, larger grains 30 to 50 nm, sharp, well defined peaks, strong, 110 texture, reduced strain. Unveiling the magnetic properties VSM and MOKE measurements. Vibrating sample magnetometry VSM measurements across applied magnetic field from minus 10 KOE to plus 10 KOE revealed soft magnetic behavior characteristic of COFE films. Saturation magnetization value ranged from 2.2 to 2.4 T depending on crystallinity and thickness. Room temperature films exhibited coercivity around 40 to 60 OE, while annealed samples showed reduced coercivity 20 to 35 OE, indicating fewer magnetic defects and improved domain structure. Magneto-optic effect MOKE measurement confirmed surface magnetization values revealed reversible magnetic domain behavior suitable for device application. Correlation between structure and magnetism. Key findings. Our analysis revealed a direct and compelling relationship between crystalline structure and magnetic performance. Films with improved crystallinity, evidenced by sharp XRD peaks and larger grain size, demonstrated superior magnetic properties, including higher saturation magnetization and lower coercivity. The 110 presential crystallographic orientation emerged as crucial as this axis aligns with the easy magnetization direction in BCC iron, facilitating easier domain reorientation. Enhanced crystallinity, reduced defect density, improved tester alignment, lower coercivity, and enhanced MS. Tailoring properties. Impact of sputtering parameters. Systematic variation of sputtering parameters provided pervasive control over magnetic and structural properties. Subtract temperature provided the domain factor. Evaluated temperatures prompted atomic mobility and crystallization, producing larger, more ordered grains. RF power controlled deposition rate and energy. Higher power enhanced crystallinity but risked subtract heating. Argon pressure affected the mean free path of sputtered atoms. Optimal pressure 5 to 10 mTOR, balanced film density and uniformity. Film thickness influenced grain size evolution with 50 to 200 nm films showing optical magnetic behavior. Temperature 25 to 300 degrees Celsius range control grain growth and crystallinity. RF power 100 to 300 watt affects deposition rate and film energy. Argon pressure 5 to 10 mTOR optimizes atom transport and density. Film thickness 50 to 200 nm range provides optical magnetic. Application and future directions. Spintronic devices. COFE films have become essential components in cutting-edge spintronic technologies. Magnetic tunneling junctions MIJs exploit the higher magnetism and lower damping of COFE for ultra-sensitive magnetic field sensors. Spin valves utilize a COFE as a reference layer, providing stable magnetic moment for reading spin-dependent resistance. Magnetosensitive random access memory MRAM systems leverage COF's soft magnetic properties for fast, non-volatile data storage. Looking ahead, research focuses on reducing damping for microwave applications, exploring multi-layer structures with enhanced exchange coping, and integrating CoFe with novel materials for room temperature operating in quantum computing architectures. Conclusion and key takeaways: structure drives performance, process control is crucial, real world impact. Structure drives performance, crystalline quality, and wanton texture orientation directly determine magnetic properties of sputtered CoF films, enabling predictable trailing of device characteristics. Process control is crucial. Subtract temperature emerges as the primary control parameters with optimized deposition enabling saturation magnetization exceeding 2.4 T and coercivity below 35 OE. Real world impact. CoFE films fabricated through magnetrons, sputtering advanced spintronic technologies in sensors, memories, and microwave devices with continued development promising quantum and AI applications. Thank you so much for giving me this opportunity.